Welcome to the lectures on fundamentals of MIMO wireless communications. We have moved into the spatial channel characteristics. We have seen how to write the expression for the CMO, MISO and MIMO channels. Now we will look into the narrowband antenna array, which is one of the important assumptions. We will also look at the classical IID channel, which is the one we are going to use mostly, and we will also look at the spatial correlation model, which will be essential in rest of the course. So, with that we will take a look at the narrowband antenna array. And in this case, let us say that we have one antenna element here and we have another antenna element here. The separation between these two is D, and we have, or rather the diagram should be better if we say the special separation is D in this direction, if this is the proper axis. So, let this be the D separation between them, and so if this is the normal to the direction, let a wavefront arrive and that wavefront be Z of t, and let it make an angle of theta with respect to the antenna array. So, clearly what we can see is that the ray to arrive at the first antenna, it takes a certain amount of time from the time it reaches the first antenna to the time it reaches the second antenna, and let this be denoted by Tz. So, this is the extra amount of time that it takes in propagating. So, this distance can be calculated to be d sine theta. You can do this expression. If this is d, then this would be d of sine of theta as per this particular geometry. So, this is the propagation, this is the distance between the antennas, effective distance with respect to the angle of the wavefront, and we will also assume that z of t is represented by z s tilde t e to the power of j 2 pi f c t. So, if we say that this is z of t, in that case what the narrowband antenna array assumption says that 1 by, or sorry, if this particular signal has a bandwidth of b, let us b be the bandwidth of the signal. In some cases you could also write it as beta of t times e to the power of j 2 pi f c t. So, if this is the band, b is the bandwidth of the signal, we would say that b is less and less than 1 by t z. This is the narrowband antenna array assumption. So, if you go by this, b is approximately, you could write it as 1 by t s is less and less than 1 by t z. That would mean that t z or t s is much greater than t z. So, what would this mean? This would mean that if I would draw the symbol duration t s, this is, let this be t s, that is the symbol duration corresponding to the bandwidth of the signal, is much larger than t z. So, if this signal arrives at the first antenna, the second symbol or the symbol would arrive at the second antenna as per this dashed representation, and this gap in time is basically t z, which is due to the propagation of the signal from the first antenna to the second antenna with reference to the angle at which it arrives and the separation distance between the antenna. So, this is somewhat similar, it is not exactly the same, but somewhat similar to the assumption that we have made regarding flat fading. That is, we said that the delays are between the multipaths are very close. So, they are almost, the inter path delay is negligible. So, here what we are saying is that the wave arriving between the first antenna element and the last antenna element, there is hardly any notable delay compared to the symbol duration. So, this is with reference to the symbol duration. So, if we say that the signal which has arrived in the first antenna is y1 of t is z of t, let's say the signal which is arrived in the first antenna is z of t, then the y of t is the signal y2 of t which is arrived in the second antenna is z of t minus tz. That means the signal which is here is z of t minus tz, or it takes extra time tz, or the signal which has started tz times before. So, that is the delay between these two antennas. So, which would be beta t minus tz e to the power of j 2 pi f c t minus tz. We will also make the assumption that there is a identical antenna pattern. That means the antenna patterns of this and this are the same. So, that means we can make the assumption beta t minus tz is approximately equal to beta t. That means the signal is almost the same, or in other words you could have e to the power of j 2 pi f c t minus tz is equal to e to the power of j 2 pi f c t times e to the power of j 2 pi sin theta times d by lambda c, that means the or d by lambda, which is the wavelength. So, y 2 of t, that means this is with this assumption we have y 2 of t is equal to beta t e to the power of j 2 pi f c t e to the power of minus j 2 pi d sin theta by lambda, which you could write this expression as y 1 of t e to the power of minus j 2 pi d sin theta by lambda c. So, if you look at the signal which is arrived at the second antenna is basically the signal at the first antenna, along with which there is a phase delay due to the effective separation between the two antennas. So, that means the signals which are arriving at the different antennas are only different from each other because of a relative phase delay, and rest of the signal is almost the same. So, this is one of the fundamental assumptions when we make antenna narrowband antenna array. That means we are saying that this distance is not large, this distance is much smaller compared to the symbol duration. So, the signal is effectively the same, but there is a phase difference in the signal when it arrives at the antenna array from the first antenna to the farthest most antenna, otherwise the signal is more or less the same. So, this is one of the important assumptions that we make, otherwise the system model would change if we do not have this narrowband antenna array assumption. With this we move on to the next important description of these kind of MIMO channels, and we have the classical IID channel. This is one of the important channels which we will use in most of our work. The classical IID channel assumes, the first assumption it makes is that the delay spread is negligible. The delay spread is negligible. In other words, the tau RMS is approximately equal to 0. So, that is what we have already said in the previous lectures, that in the rest of the course we are going to make this assumption. So, this is basically referring to one of the conditions of the classical IID channel. The second one it states is that the H with these two underlines indicates the MIMO channel can be modeled as zero mean, Zm is zero mean, circularly symmetric, complex Gaussian with unit variance. Okay. So, this will describe a little bit. Zero mean means the each of the components of H are having a mean of 0. We have already seen, let us say we have H I comma j as one of the component. We have seen the situation where H I j is the mean of H I is 0, and that means there is scattering from all directions. So, that is the one of the cases. Circularly symmetric would mean that it is complex Gaussian. That means if it is z is represented as x plus jy, these are real Gaussian and they have 0 mean as well as they have the same variance. So, that is the circular symmetricity leads to us, and they are independent of each other. And complex Gaussian is of course this particular expression. Circular symmetricity usually would mean that expectation of e to the power of j phi for all real phi of z is equal to e to the power of j phi and e of z, which leads to e of z being equal to 0. So, that means effectively we have this as the channel coefficients, where x and y components are independent. We have seen that phi, h, q, h I, delta t, they are uncorrelated, equals to 0. This is what we have seen, and we have seen that h q and h I are Gaussian, both are Gaussian. So, for two Gaussian random variables which are 0 mean and they are uncorrelated would mean that these are independent. So, in our case we have h I and h q components are independent. So, if they are 0 mean and they are complex, so basically it is a 0 mean circular symmetric complex Gaussian representation. So, this condition satisfies, and in other words we are basically stating that expectation of h w, we will describe what is h w. We are basically talking about h w in terms of spatially white. So, w indicates white, you know about white Gaussian noise. So, white means in the space dimension there is probability of rays arriving from all directions with equal probability. So, h w I j, that means for this matrix ith I comma j element, that means ith row jth column element, expectation of that is 0. This is one of the first thing. The second thing is, once we have said the mean is 0, we would say that h w I comma j, the mod squared value of it is 1, that means it is unit variance, and it is circular symmetric, that means uncorrelated or spatially white. Sorry, we are talking about this classical IID, that means it is independent, identically distributed, independent and identically. So, what we have is h w I comma j, h w m comma n conjugate, if you take this product, is equal to 0 if I is not equal to m and j is not equal to n. So, that means if I take this matrix and if I take any two elements and we take their product with the conjugate of 1, that means projection of one on the other, and take the expectation, or we are taking the correlation of them, they are uncorrelated with each other, they are being Gaussian, they are being independent. So, basically we are saying they are spatially white, and that is being indicated by the h w that we have over here. So, this describes the classical IID channel, which is one of the very important channels that we use in deriving many of the results. So, we have seen two very important characteristics or two very important descriptions of the MIMO channels which we are going to use. Next we are going to look at the spatial fading correlation. So, what we have described is a white channel, that means it is uncorrelated, all the points are independent. So, now we have to look at the correlation, because we said if antennas are spaced so that this is less than the coherence distance, there would be correlation in the signal, elements of H are correlated. So, basically we are talking about H, the channel matrix which is having correlated elements. So, this is modeled as vec of H. This is the vectorization of H. H is a matrix, we will describe how to vectorize it, is R, which is the covariance matrix, a square root of that times vec of H w. In other words, it says that if I can generate H w, that means a spatially white channel, and I have this correlation model, then using this, or rather if I have this, I can generate a H w, and this would bring in correlation amongst the elements. I would generate a channel matrix which would be correlated. So, this is a spatially white channel. Using the covariance matrix, I could generate a spatially correlated channel coefficients, which will be useful in performance analysis. The vec operation, it basically stacks the columns of A. So, suppose a vec of A is what we are interested in, and if A is equal to A1, A2, this is a column, this is a column. So, I put it as an underline underscore indicating it is a vector up to let us say A n. So, this is a matrix, this is a column, this is a column, this is a column, these are all vectors. So, this is a matrix. Vec of A would be the operation A1, A2. So, this is the whole column, this is the whole column up to A n. So, A1 stacked above A2, stacked above A3, and so on and so forth. So, this is how you do the vec operation. So, with this you could generate this particular H, and from vec of H you could get back to H. So, HW that we have over there is a spatially wide MR, sorry, it is a MR cross MT channel matrix, and R is MR MT cross MR MT covariance matrix, and R can be obtained as E of vec of H times vec of H Hermitian. Look at this. So, basically if you have H, from H you could get R. So, this is another way of stating it. So, if I have R, then I could get H. If I have H, then I can get R. So, this is either way of going from HW to H, or from going from H to R. So, this is the expectation, means over several realizations of H you could get the covariance matrix, and this being a Hermitian matrix, you can clearly see this is Hermitian matrix. So, R, the covariance matrix is positive semi definite Hermitian matrix. What does it mean? It means that it is Hermitian. Hermitian means if you take A, if Hermitian means the Hermitian of A would be equal to A. So, that is a Hermitian matrix. Positive semi definite would mean that all the eigenvalues of H are all greater than or equal to 0. So, that is what it means. Of course, there are more description. So, from this point onwards, as you can clearly see, we are using some of the results of linear algebra. So, again at this point it would be very crucial if you could revise some of the important formulas from linear algebra, which will be used quite often in this case. So, now we can see is that if R is equal to I MRMT. I MRMT means it is an identity matrix of dimension MRMT. That means identity matrix is the one where only the diagonal elements are 1, rest of them all are zeros. So, that means what it says is that it is correlated only with itself, and the result of correlation is 1, which is pretty natural. When you correlate with any other element, the values are all zeros. So, that means it is 1 1 1 1 0 0 0 0, all zeros except the diagonal elements all are zeros. So, that means any cross correlation term is 0. So, if this is the case, if it is uncorrelated with any other element, naturally it means that what we have is HW. Clearly, if this is identity matrix, even if you go by this, if it is identity matrix, then H is equal to HW, straightforward from this also. So, in other words, it is basically bidirectional that we are trying to explain. If you get R as identity, that would mean that you are dealing with a spatially white channel. Instead of this, sometimes another way of describing the correlation is also followed, where it is simplified in terms of H is equal to the receive covariance matrix raised to the power of half, HW the transmit covariance matrix raised to the power of half. That means you have HW, one has measured the receive covariance matrix or the inter antenna correlations because of the spacing and the scattering environment, and the transmit antenna covariance. So, if I have these two measures separately, again using HW you could generate the H matrix which has correlation. So, RT is MT cross MT covariance matrix, this is MR cross MT, and this is MR cross MR covariance matrix. So, both since these are covariance matrices, these are again positive semi-definite matrices. So, we can use this method or this method to arrive at H, which would be having spatial correlation. Now, the relationship for connecting RR, RT and R would be R is equal to RT transpose Kronecker product with R of R, where a Kronecker product would be defined in a way that let A be a N cross P matrix and B be a M cross Q matrix. If A and B are two such matrices, then the operation A Kronecker product B would be defined as A11, which is the first element of the matrix A, times the matrix B, then A12 times the matrix B, and so on up to A1P times matrix B. Here it will be A21 times matrix B up to AN1 times matrix B. Matrix B is of the size M cross Q, this is N. So, definitely this whole product is Mn. So, you can clearly see M number of elements here, N number of elements here, Mn cross. You can guess the next one. This is P, this is M cross Q. So, P and Q would lead QP. So, this is the dimension of the Kronecker product that we get. So, here what you would get is MT cross MT, MR cross MR. So, basically MTMR cross MTMR is the size of R, which is already described as the one of the R particular matrix. So, this way we could add correlation properties into the channel matrix, which is otherwise spatially white. Now, this H W, the channel that we will be using in our case, is having the property that HW is a full rank matrix with probability 1. This is a full rank matrix with probability 1. This is very important to consider. So, this we should remember that HW is random. HW is random because it contains MT cross MR number of elements. Each of the elements are complex Gaussian, zero mean and circularly symmetric. So, that is HW entries. So, it can form a matrix because it is a random matrix which can have certain amount of correlation. The moment there is a correlation, rank is no longer a full rank matrix. So, what we are saying is we are taking the channel contents or the channel elements of HW in such a way that it is a full rank matrix with probability 1. So, if we are using HW, it will be the one which is full rank. In presence of, if there is any correlation, if there is any transmit or receive correlation, the rank is modified and constrained by the rank of RR or that of RT. So, it is constrained by the rank of RR and RT, and then the rank of the matrix is less than the full rank of HW. We will see many things in details later on. With this, we would move on to some of the statistical properties of HW. This is somewhat important. So, if we have HW, or sorry, we are talking about the statistical properties of H, that means the channel matrix. So, H is MR cross MT matrix. So, you can break down H into U, D and V Hermitian by means of singular value decomposition. So, if you do a singular value decomposition, you are going to get D as the diagonal matrix, and U and V are such, they are unitary matrices such that U times U Hermitian is equal to V Hermitian times V, which is equal to I of order R, where small r is the rank of H. R is equal to rank of H. This is how the relationship holds. So, if you do singular value decomposition, you are going to get D as the diagonal elements. You would write it as the diag sigma 1, sigma 2 up to sigma r, with sigma I greater than or equal to 0 and sigma I greater than or equal to sigma I plus 1. That means the diagonal elements are arranged in such a way that the first element is greater than the second element and dash dash up to the last element. So, the last element is the lowest singular value, and all of them are greater than or equal to 0. So, they are non-negative. That is one of the outcomes of this particular process. And if you look at HH Hermitian, HH Hermitian, this is MR cross MT, this is MT cross MR, this is MR cross MT size. This size is because of the Hermitian operation, MT cross MR. So, naturally this whole product is a MR cross MR. This is a Hermitian matrix and it is positive semi-definite. So, it being positive semi-definite, again the product of the eigenvalues are greater than or equal to 0, and these HH Hermitian you could decompose into HH Hermitian, you could decompose it into Q lambda Q Hermitian, where lambda is the diagonal matrix consisting of the eigenvalues H1 lambda 1, lambda 2 and up to lambda MR. So, these are the eigenvalues of HH Hermitian, and lambda i's are greater than or equal to 0 and lambda I is greater than or equal to lambda I plus 1. Again a similar thing like the singular values. So, with this we further have the description that lambda I is equal to sigma I squared if I is equal to 1 to up to R and is equal to 0 if I is equal to R plus 1 up to MR. So, what we have said here is that whether we look at the singular values of H, that means here we have H from which we have arrived at the singular values, or we take the HH Hermitian and we arrive at the eigenvalues of HH Hermitian, they are related to each other in the form that lambda I, the eigenvalues, the ith eigenvalue of HH Hermitian is equal to square of the ith singular value of H. So, this is the relationship that we can use in all our expressions that we will encounter in future. And when we talk about the singular values or singular value decomposition or the eigenvalues in this, when we do the eigenvalue decomposition, we will assume the first eigenvalue is greater than the second eigenvalue and so on up to the last eigenvalue, and they are all greater than or equal to 0. Now, this positive semi-definiteness of this HH Hermitian and HH Hermitian, you can or this R matrices or this R matrices, that means RR or RT matrices, you can easily verify from the first principle. That means if you set out with let H be equal to H11, H12, H21, H22. Suppose you set up with certain H, you will arrive at conditions where you are going to get that this particular product HH Hermitian, this particular product is having only terms which are like mod squared terms, and mod squared terms are greater than or equal to 0. The minimum value that mod squared terms can get is 0. Otherwise, it cannot take negative values, and that's another reason why you would call it positive semi-definite. And now, one more thing to remember, that since H is random, because H is random, because H is made up of H11, H12 up to H1 MT, H21 up to HMR1 and HMR MT. Each of these are random. That's what we said. These are zero mean circularly symmetric complex Gaussian. So these are all random. Therefore, H is random. If H is random, so are the singular values and so are the eigenvalues. So we should remember that these are all also random values, and what we will briefly look at in the next lecture is about the distribution of these eigenvalues and that of the minimum eigenvalue of H. So that would give us a description about the H channel, which is the MIMO channel coefficient. So that's all for this particular lecture. In the next lecture, we're going to see the distribution of these lambdas and also one particular moment generating function for Frobenius norm of H, which is also very important, which we'll be using in the bit error rate calculations. Thank you.